Here is the improper definition. Here is a definition again for the improper integral of first kind. And of course, what we do for the upper limit, we can also do for the lower limit. So if the lower limit is infinity, or actually minus infinity, then replace the lower limit with a limit. Okay, now we call it a, and then we send a to minus infinity. And again, we can talk about divergence or convergence, depending on what the result is. So here, quick example, quick and dirty. So this is then the limit. Now a goes to minus infinity. So we go from a to minus 1 over x squared dx. And then we integrate this, keeping the limit, first of all, a goes to minus infinity. And then we have a definite integral of 1 over x squared. So the antiderivative is minus 1 over x. And then evaluated between a and minus 1. I know it is cumbersome to carry the limit sign all the time, but it's actually necessary, so we have to do that. I sub in minus 1 first, so I get 1 over 1 plus 1 over a. And now a goes to minus infinity, which means this term here actually goes to 0, and the result is equal to 1. Just on a side, what did we compute? Well, let's plot the function. 1 over x squared is looks a little bit like this. It's a hyperbola, which is always positive, so it is here and here. And then integrating from minus infinity to minus 1, so let's say here's minus 1, then which means we have the area under the curve all the way to the left to minus infinity. But all this area here turns out to be equal to 1. Here's another interesting case, which is doubly improper integrals, meaning that we have infinity here and here, right? In this case, we split the real line into 2 bits. We go from minus infinity to an intermediate value c, and then we continue going from this intermediate value c to plus infinity. And this can be done for any number c, and then of course often, mostly all the time, we choose c is equal to 0, like in the next example. Evaluate if it converges the infinite limit from minus to plus infinity of dx divided by x squared plus 1. The idea was to split it first into 2 bits, so I write it from minus infinity to 0, dx over x squared plus 1, plus the integral from 0 to infinity. See, I did use c is equal to 0 here. And then each of these integrals I write as a limit. So the first one I need to write to be limit a to minus infinity, integral from a to 0, dx divided by x squared plus 1. And the other limit is limit b to infinity, integral from 0 to b, same function. Okay, so then we can integrate these functions. We have definite integrals. And looking at our integral tables, we find the formula that the antiderivative of 1 over x squared plus 1 is the arctan. Arctan. Okay. So then we have this is equal to limit a goes to minus infinity arctan of x evaluated between a and 0, and then plus another term limit b to plus infinity arctan of x evaluated now between 0 and b. We get limit a goes to infinity arctan 0 minus arctan a, and then plus limit b to infinity arctan b minus arctan 0. Now to be able to go to the limit, we need to know something about arctan. And I just show you a sketch here how arctan looks like. And so it comes from here and goes to 0 and goes there. And these asymptotes, this is minus pi over 2. And this asymptote is plus pi over 2. So meaning at 0, this function is 0, so these two terms disappear. And then as a goes to minus infinity, then minus arctan goes to minus pi over 2 with a minus sign. Okay, so the first term is minus pi over 2 from the arctan of a. And then the b term, as b goes to infinity, arctan goes to pi over 2. Pi over 2. All right? So together then with the two minus signs there is a plus, so we get pi half plus pi half, so the result is equal to pi. To summarize, we can add 2 formulas to our first kind improper integrals. First here we had the upper limit, which we did in the previous video, where we replace the upper limit through a limit. We can replace the lower integration limit if it's minus infinity with the limit a to minus infinity. And if we have them in both in the bottom and in the top, then we need to split. We split the integral into 2 bits, where one is from minus infinity to c and the other from c to infinity.